Good morning. Welcome to Krishna's class. So after quite some time that we are meeting again. In fact, I was away for some time and now back to take over to carry out the mission once again. I hope we will be meeting more frequently now, from now on. Yeah. So what is the topic that we are going to discuss in the next few lectures? Now we have already seen some representation theorems for non-negative linear functionals on C naught x, where x is a locally convex, where x is a locally compact space and it's a Hausdorff space. Now for such functions, on such functions which form a linear space, that is functions with compact support, we not just that, this is the functions which die down at infinity, or what you call such C naught x functions. On that, because it's a linear space, we can define linear functions. And for non-negative, or rather positive linear functionals on C naught x, we are characterized by the Rees representation theorems. And the difference now is that there we are talking about real measures representing. Now what we do is we try to go for an extension, not an extension in the true sense, because we are now going to talk about bounded linear functionals. Okay. Earlier the restriction that we had was positive linear functionals. Now let us recall a few facts before we state the theorem. And we define a few things. One, X is a Hausdorff space. If for P Q belonging to X, P not equal to Q, there exists open neighborhoods U and V of P and Q respectively, such that what it says is the following. This is the space X in which you have a topology. So there is an open set, concept of open sets there. It says that if you take any pair of points where P is not equal to Q, there exists open neighborhoods U and V such that U intersection V is That means there is a well-defined separation rule in the space. So such spaces are called Hausdorff spaces. So we start with a Hausdorff space. That is one of the basic things. Now we define what is called a locally compact space. Locally compact space if every point of X has a neighborhood whose closure is compact. Well, let me tell you exactly what we are trying to do is to go for generalizations of real line, the usual metric. Okay, so we are generalizing the whole concept, and we are not. We are now talking about what are called a locally compact Hausdorff space, which means if you have a point P, yes, an open neighborhood whose closure is compact. That means you have a U, P contained in U, or P belongs to U, U open, and U closure is compact in the usual sense. That means every cover has a finite subcover, usual compact. So this is the basic structure that we observe on R with the usual metric. Okay, right? So we are trying to generalize this, or take Rn and the usual metric, you get these examples. So we are generally working on what are called Hausdorff spaces. So we assume X is a, so we take locally compact Hausdorff space. Talks about a local structure, and it also talks about a separation property that is attributed to X. So we are going to work on such spaces. So we'll just recall the theorem for positive linear functions. CCX is the class of all continuous functions, continuous real valued functions, because we are going to talk about positive linear functions. Okay. So we work with complex linear functions is all right. Sorry, not positive. We are talking about a positive linear function. We can talk about complex value continuous functions on X, where X is a locally compact Hausdorff space. Okay. With the compact support, that is the notation for CCX. Okay, so CCX is the set of all continuous functions defined on X with compact support. Okay, so let X be a locally compact Hausdorff space. Now we look at consider all positive linear functionals on X. Sorry, on CCX. What is CCX? Set of all real valued or complex valued functions on X with compact support. Compact support means the set on which the function is not equal to 0 is just a sort of, we will just recall these little things, that is we recall the following facts, that CCX, all continuous functions, on X what do we mean by compact support? Okay, the compact support is support of F is defined by the set of all X not equal to 0, the closure of that. Okay, and what we demand is that support of F compact. This is what we ask for. Now we take C naught X. It's defined as the set of all F X to C complex valued functions with the property that for every epsilon positive there exists a compact such that mod F is less than epsilon on K complement. That is the complement of K. This is what you call C naught X. Now you see that CCX is contained in C naught. C naught x, and also with this property, with the norm which is well defined, namely when you take function with compact support, then this is going to be over the support of f. Okay, so I can write here, in fact, support of f. Okay, which is the same as the other one, and this is the norm with the norm is a Banach space. That means it's a complete normed linear space. That means all Cauchy sequence of elements in C naught x converge in the same space itself. Okay, and what we have is further closure of CCX equal to, that means the following, that CCX is dense in C naught x. The Cauchy sequences in CCX may not converge in CCX itself, but the limit certainly belongs to C naught x. Okay, and every element of C naught x can be obtained as the limit of a Cauchy sequence in CCX. Now this is what you mean by the closure of CCX is equal to C naught x. This property is satisfied. Okay, and this is a Banach space, whereas this is not. So completeness property is satisfied. Okay, so we will use that later. Now we write the positive linear functionals, and then just to recall the representation here. For positive linear functions, which means the following: should take a positive element, a non-negative element of CCX. Okay, right? Then the action of lambda on that will give you a positive number, and lambda is a linear functional on CCX. That means lambda is a linear map from CCX to R. Okay. Positive linear functional which has this additional power. Okay. So let CCX. Then the following are true. A, where exists a positive measure mu such that lambda f, this is the representation here. And this is unique. Okay, it's a unique measure. B for all compact sets K contained in X system. For all compact sets K, the measure of K is finite. The sigma algebra M mu E equal to infimum of mu of V E contained in V open. These are the connection of or what is called the measure of a measurable set in M. The mu E is also equal to supremum of mu of K. The K is contained in V and K compact. Compact for every open set finite. Mu E is finite. Now D is the representation theorem that we have proved. If E belongs to M, equal to 0, then A belongs to, that means all subsets of measurable sets are measurable if mu of E is 0. Okay. E is an open set. if E is a measurable set and A is contained in M, then mu of E equal to, that means for all measurable sets with measure 0, every subset is measurable, and needless to say that mu of A equal to 0. That's also. So this is what we have. What does it mean? It means the following. Consider all positive linear functionals on CCX. Okay. So you take CCX So you take any positive linear functional on CCX. Now you can easily see this. What happens? Okay, you take this one. So given lambda, a positive CCX, lambda induces a measure or in other words what we have is this. There is a sigma algebra M that you have, which is governed by these rules. That means you have X mu, where of course lambda f is equal to integral over x for every f belonging to CCX. Okay. Right? And all the measurable sets are given like this. Okay. Right? So what you have is you have a measurable class of measurable sets which consists of all Borel sets. Okay, and you have Borel sets are the collection of the sigma algebra which contains all open sets. So all open sets are there, therefore all Borel sets are there, and you see that the measure of an a open set E is defined by D. Sorry. Defined by D, and that means you are approximating, you are able to approximate the set, the open set E from inside through compact sets. Okay, right? And of course, this is mu of E is defined in this way, that is the infimum of mu V. So all measurable sets in M, you can approximate from inside using open sets. Okay, so this is how the measure is. So C defines the measure. Okay, so lambda corresponding to lambda, you have and conversely, if mu is, if M is a set of all moral sets on X, and mu is a given positive given measure of that, then it gives you it defines a bounded linear, defines a positive linear functions on C. So this is the connection. Okay, so all positive linear functions determines a measure, and you have a measure with certain properties, then it's going to be induce a positive linear function. So either way, this is true. Okay, so this is the identification, and this measure is unique. Therefore, this is a unique representation theorem, and which is the well-known Viswa representation theorem. Okay, for all positive linear functions. Now, this we have proved. Okay, to recall that very elaborate discussion we had earlier on this particular topic. Now, at that time, we had not thought about the complex measures, and after that, we introduced the concept of complex measures and so on. And in the light of what we have done so far on complex measures, we are going to ask what kind of representation theorem is possibly valid for complex measures, or for bounded, I mean, see which linear functions are going to be represented by the positive. Okay, the clue is this: if mu is a complex measure, then you see you have this representation theorem. You have once again the representation theorem. FDU, and then you see that the for F belonging to it's a Banach space C dot. Okay. If you have a complex measure, using that you can define a complex linear function, and that's a bounded linear function on C naught X. Now this is the unique representation theorem that we are going to prove in the general case. Now let us work on that. So characterization of bounded functions. The next step is bounded linear functions. We are not insisting that should be a, we are not working on positive functions, but bounded linear functionals. A similar result like the one for positive linear functionals is valid. Now you see the function, the measure that is determined is going to be a complex measure. Okay, so that is the connection. So you have three things here. One, x, then you have got CCX, which I will argue soon that we can work on C naught x, and then you have got bounded linear functions. This is the class of bounded linear functions. Now every phi, corresponding to every phi, you have got xn, where mu is a complex function. Uniquely different. And the converse and the representation is through this by the relation phi of f Okay, so this is the content of the here. So let us write this. So CCX is a dense subspace of P naught. Okay, it is dense in the sense that CCX closure is equal to C naught. That means every element of C naught x can be approximated by as closely as you want with a function in CCX. Okay, and this is dense, CCX is dense in C naught x. With of course the super. Now suppose let phi be a bounded linear functional on CCX. And CCX is dense in C naught x. Therefore, what you can do is the bounded linear functional phi has a unique extension to, so phi has a unique extension to a bounded linear functional on How do you get that? Okay, phi is a bounded linear functional on CCX. Okay, so now what one does is take any then there exists a sequence CCX such that well, this is a soup now. So if you want, I can put this because this stands for use this norm, then this is going to be 0. So there is such a sequence. Now what we have phi of f converges to phi of f, because what you have is this phi of because it's a bounded linear function. Okay, therefore phi of f goes to phi of f and as n tends to this goes to 0, then goes to 0. Therefore phi of f is defined as the limit of fn, where fn converges to, okay, and such a extended phi on is linear and bounded. Therefore, without loss of generality, we need not stick to CCX. Okay, so here, and of course C naught X is a Banach space. That means it is complete, and CCX is a dense subspace of the Banach space. And instead of we shall we can talk about all bounded linear functions on C naught. Now we will put the whole thing back. We have already seen that if mu is a mu is a complex Borel measure, Borel measure means the measure the measurable space M consists of all Borel sets in C. Okay. So that the entire topology, it's a measure space built on the topology that is already existing on X that we are talking about. Okay, because all open sets are now measurable. Now you see that all open sets measurable. Then there exists a complex Borel function that means complex valued function defined on Borel sets H mod H equal to 1 such that we have seen that if mu is a complex measure, then what we designate as mod mu is the total measure that we define on X with the same measurable sets and so on. And you can represent every complex measure in terms of the total measure. Okay, and there exists some H with mod H equal to 1. That means the absolute value equal to 1 such that d mu equal to H, the total measure of reasonable to, right? Now a special case of is the characteristic function of measure of, okay, and further you can show that this is we have the following is true: integral over X chi for two measures mu and lambda mu plus lambda is a measure this is equal to and this is equal to lambda e and which is equal to integral over chi e complex measures on M so this gives the addition formula. Now you see that integral over x equal to by 3. Mark this like 3. Now this is valid for all counted measurable f on now we will just introduce what is a regular formulation. Now we define the following regularity. A complex Borel measure mu on x is regular, is a real measure. What mu is a real measure. So we just recall the following. Defined on a sigma algebra of all Borel sets in a locally compact Hausdorff space X is called a Borel measure on X. So that's about the Borel measure. If mu is positive, a Borel measure a Borel set E is outer regular we are talking about a positive Borel set. A positive Borel measure, and a Borel set is said to be outer regular if the following condition holds. What is that? That means E can be approximated, the measure of E can be approximated through measures of V from inside. So this is the from outside. So what you have is this is your E. Now E is inside a open set containing E, and you take a mu E, then mu E is essentially the infimum of mu V for all V containing, that is the then it is called outer regular. And is said to be inner. Mu is positive and inner regular if mu e supremum of mu k complex. K complex. So you are essentially approximating the measure of E from within using the measures of compact sets contained in that. Okay, that is the meaning of it. So you have got an outer regularity if it can be approximated from outside using open sets and in measure, and it can be approximate the measure of E can be approximated from within using compact sets contained in by taking the supremum. Okay, so therefore we have got both inner regularity and outer regularity. Now we can write the two classes of sets that you have, all open sets as well as every set in M whose new measure is fine. Now this is what you call inner inner regularity. So now we can say, what is this? If every Borel set both outer and inner regular, we say mu is this is for positive measures. This is for positive measures. Okay. So this is the what you have for positive measures. Now, how do we extend the notion of regularity to complex measures? Because we have already seen that d mu can be written as some h, a complex valued function with absolute value equal to 1 in u. So you see that we say that mu is regular if the total variation measure is regular. Okay, this is a complex measure, this is a real measure. So that's the definition. that we have already seen. So mu is regular. Equal to 1. Now look at this one. Consider the linear functional defined by it is equal to dv. This is well defined. So through this you define. Then phi is a bounded linear functional on C naught x. Okay. And the norm of phi then defined as is bounded by total variation of. Okay, this is the bound of the linear function. Right? Now let us. So the question is this. When a bounded linear function x, does there exist a measure mu such that This is the question that we are going to. In fact, the theorem, this is called the representation theorem, essentially answers this. Answers this in the affirmative. So let me just give the statement of the theorem and then conclude today's talk with that. So if locally compact Hausdorff space it's a topological space which has the separation structure of Hausdorff space and it is locally compact. Okay? As we have defined earlier, then every bounded linear functional on C naught x is represented by a unique regular complex measure mu sense the sense that first statement moreover the bounded linear function. Therefore, what is the norm of that? The norm of is the total variation of that is so that is the statement of the theorem. So given a bounded linear function, there exists a, and given a regular complex function, you have it determines a bounded linear function. So this is the relationship between this bounded linear function and the measure. regular measure that you define is what you call one identifying. And this is a unique representation theorem that it's a very powerful result, which not quite generalizes the previous representation theorem, because there we were talking about all positive linear functions and not necessarily bounded. Okay. Here we are talking about bounded linear functions, and that is the situation when we deal with complex measures. I have also made a remark about this earlier. Okay. So, thank you very much. I will continue with it with the proof of this theorem. It's a longish proof with various stages. So we will start working on the proof of this theorem in our next lecture. Thank you very much.